Searching is something that we take for granted nowadays. We expect to find what we're looking for in seconds thanks to powerful search engines like Google. Imagine having to sift through billions of websites by hand. It would be an impossible task. So, how does it work? Well, one way to search for text is to check each character in the input string against each character in the target string. This is what it might look like if we searched for the text round in the target text, rain on brown ground. The strings are aligned at the start, and the first character is checked. R matches R, so the next character is checked. A does not match O, so there cannot be a match in this position. The search string is moved along before checking from the first character again. A does not match R, so the string is moved along. This continues all the way down the target string until a match is found. This simple approach works, but takes a long time. Let's look for a shorter method. What if we could reduce the number of comparisons that we needed to make? How about searching for matches, starting with the last character of the search string? Space doesn't match D, so we can move the string along. Or we could notice that space doesn't occur in the search string at all. This means that we can move the search string further down the target string, all the way past space without missing any matches. If we can skip over characters rather than comparing them, we can save time. Again, matching from the last character forwards, R doesn't match with D. How many characters can we skip this time? Well, we can't skip over as many as before because R is found in the target string and we might miss a match. We can only move 4 characters down as far as this R match because it might be a match of the whole string. In this case it is not, as space doesn't match D. Again, we can skip over 5 characters. N does not match D, but N is found in the target string somewhere. We move the string along to this match and check again. This time, all the characters are the same, and we have found our match. This approach is called the Boyer-Moore-Horspool algorithm. It is a simplification Nigel Horspool made to the Boyer-Moore algorithm. To get this algorithm to work in practice, we need a way for the computer to calculate how many characters to skip when there is a bad match. A fast way to do this is to generate a table. Each row in the table represents a character in the target string, with the question mark meaning default when the character is not otherwise in the table. The table is filled with values starting with the default, which is set to the length of the search string. In this case, it is 5 characters. The length of the search string is used because we can skip over the whole string's worth of characters if a character is not in the search string. The other values are filled, starting with the leftmost character, using a simple formula. The number of characters to skip on a bad match is equal to the length of the search string minus the number of the character we're looking at. So with R being the first character, it takes the value of 4. This is because if a bad match is caused by an R in the target string, we can only skip until the next R match. Following this formula, we can generate the skip values for each character. Would D then have a skip value of 0? If we give any character a skip value of 0, the search string won't be moved along at all, and we'd end up stuck in an infinite loop. The rule is that we don't include the last character of the search string in the table. The algorithm can now use this table to see exactly how many characters to skip without doing any extra checks. The table is small and very quick to build, so this is a huge benefit in speeding up our search. Let's look at a slightly more complex example and follow it in the order the algorithm works this time. In this example, there are 2 instances of the letter O in the search string. O can't appear in the table twice, so which value should it take? The formula of length of search string minus the number of the current character still applies, but O gets overwritten the second time. So, following from the left, the default string gets 4, R gets 3, and O gets 2. O then gets overwritten by 1. This overwriting ensures that we skip to the rightmost character that matches and don't miss any possible matches. Now the table has been generated, the algorithm can begin to match characters. Apostrophe doesn't match M, so we move along the default amount of 4 characters since apostrophe isn't in the table. O doesn't match M, so we look up O in the table and skip 1 character. Space doesn't match M, skip 4 characters. O doesn't match M, skip 1. Space doesn't match M. Skip 4. Again, space doesn't match M. Skip 4. In this position, we have found our match. This example showed that by overwriting repeat characters in the skip table with smaller skip values, we still produce the correct result. A quick note on the algorithm's complexity. The average runtime of the Boyer-Moore-Horspool algorithm is in the order of n, whilst the first simple method is n times n, where n is the length of the search string and m is the length of the target string. This is a considerable speed up for a relatively simple algorithm. That's the end of this overview. Thanks for watching.